there we go. Let's review some of these polar graphs. And so we're going to actually kind of switch back and forth between this polar graphing page in our notes and then the calculator. Because you actually have a calculator, your calculator has a polar mode in it. Of course, we're going to want to make sure that we're also in radian mode. Like, we really don't ever want degree mode for these calculus classes. So always make sure you're in radian. Let's go switch it over and let's go look at our calculator in polar mode. And we're going to graph these first couple. We got 2 cosine theta, 3 cosine theta, negative 3 cosine theta. We're going to graph all 6 of these pretty quick and then try to see what do we notice about all of these graphs. Let's go switch it back. There's my calculator. Now let's switch it. I just hit the mode button. Of course, we're going to need to be in radian mode. That's already good. And then I have already switched it over. But you could just scroll over. We have function mode, which is when we have y's and x's. Typically, we do most of our work in function mode. You could also switch it over for parametric mode for whenever we did the parametrics. Although really, we don't need to use the calculator a whole lot for parametric mode. But if you want to graph stuff parametrically, you could. And then we have polar mode, and then we don't really fuss with the sequence mode, although we could have when we did the sequence unit. We just don't usually have calculator questions in that. But yeah, we're in polar mode, so that's good. That means instead of y equals, we're actually going to see r equals. And instead of getting x's, we're going to get thetas. Now again, that button x, that's really the variable button. You'll get x's when you're in function mode. You'll get t's when you're in parametric mode. You'll get thetas when you're in the polar mode, and you'll get n for the sequence mode. That's why there's x, comma t, comma theta, comma n, right? That's the variable button. Depending on which mode you're in, it'll determine which one you get. But that first graph that we wanted to do is 2 cosine theta. And let's look at what this graph is going to look like. And it's a circle. And it's a circle on the positive x-axis that extends out to 2. All right, so let's look at this, switch it back. It was a circle that looked kind of more, that was really bad. That was slightly less bad, but it was a circle. It was on the positive x-axis, and it actually extended out to x equals 2, extended out 2 units. Let's look at 3 cosine theta, right? What do we think 3 cosine theta is going to look like? Well, if I go to this and I just type in 3 instead of 2, guess what? It's going to be a slightly bigger circle. It kind of looks like an oval. Sometimes the graphing, just because of the aspect ratio, the graphing looks a little bit weird. I think if you hit zoom, zoom square. Let's see if that works. Yeah, if you hit zoom 5, if you square it, then it actually looks like the circle that it's supposed to be. The regular aspect ratio kind of looks like more like an oval, but if you hit zoom square, then there we go, right? It is a circle, but that one's going to go out to 3. Right, so that one's going to go out to 3, but it's on the positive x-axis. The only thing different here, since it's negative 3, is that one's going to be on the negative x-axis, right? It's going to be on the left side. We could go back to the calculator to look at it. Let's insert that negative. Make sure you don't hit the minus. Make sure you hit the negative sign. There we go. And then if we were to graph it, poof, that circle has moved over. And if we wanted to do, instead of cosine graphs, if I wanted to do sines instead, right? So if I did sine of theta, guess which axis is going to be on? Well, the y-axis. So a negative 3 sine theta would go 3 units down in that y direction. It'd be on the bottom side of the y-axis, and it goes 3. Or if we had positive, let's say positive 5, it's going to go up 5 units. But anytime I have a cosine or a sine graph, they're just going to be circles. So let's go back to these notes, right? 2 sine theta, since it's a positive sign, it's going to be on that positive y-axis. It's going to go up 2 units. That was, again, pretty terrible. So there we go. 3 sine would go up to 3. The negative 3 would be on the negative side. So what do we notice about all these graphs? Well, they're circles, right? All of these polar equations where I have r equals, it could be plus or minus, but I have a, and it could be a sine or a cosine. Anything that fits this formula is going to end up being a circle. Now, whether it's a sine or a cosine, that will tell us which axis that circle is going to primarily be focused and centered around. Right? A sine equation will be on the y-axis, and the positive or the negative, that's going to tell you which side of the axis. So a positive sign is going to be up on top. The negative sign would be on the bottom. And then if you had a cosine, it would be on the x-axis, so either on the right or the left. Again, sine or cosine tells you which axis. The plus or the minus tells you which side of the axis. And that a, you got to be careful. That a is not the radius. that A is actually kind of how far it extends in that direction. So it's really the diameter of your circle. But all of those are circles. Some of them are on x-axis, some of them are on y-axis. Again, kind of the key things to remember. This is going to tell you which axis it's primarily kind of centered around, and then this is going to tell you which side of the axis. Positive cosine right, negative cosine left, positive sine top, negative sine bottom. Right? But all the stuff that's just a number and then either a sine theta or a cosine theta, those are all going to end up just being circles. Those are some of the easy polar graphs, right? Some polar functions are easy. Some of them are slightly less easy. And we actually have another way of getting circles. If I just have something like r equals 5, that will also be a circle. And let's go look at that just really quickly. We don't typically see stuff like that. But if we had something that was just r equals 5, that will also be a circle with the radius that's 5. Or if we had something like r equals 2, that's going to be a circle centered at the pole. The word pole is the polar mode equivalent for the origin. So if I have r equals a number, that's also going to end up being a circle. R equals 5 would be a circle with the radius of 5. R equals 2 would be a circle with the radius of 2. And so r equals any number, that will also be a circle. That's going to be centered at the pole. That's a terrible at, with the radius equal to whatever that number is. So we actually have a couple different ways of doing circles. We could do circles on one of the axes. That's what the orange equation looks like. Again, sine or cosine tells us which axis. Plus or minus tells us which side of the axis. Or we could have r equals some number, and then that's going to be a circle centered at the pole with the radius of that number. Just be careful though. Remember that's not the radius. That tells me how far along the axis that circle is going to extend. Very good. Let's kind of close the door. We're going to wrap the bow on circles. We're going to move on. We're going to look at the next type of graphs. Now, you guys should have seen these a little bit in Precal. I know that was probably quite a bit ago for some of y'all, like 2 years for some, maybe just 1 year ago for a couple of y'all. But yeah, these polar graphs, you would have seen them and then not really done a whole lot with them because you don't really use polar stuff in Precal that much. You don't really use it in Calculus 1 at all, but you use it more in Calculus 2 and beyond. Because Calculus 1 really focuses on things that are functions, things that like, hey, are y based on x, or occasionally we get x based on y, but mostly we get things that are functions. These polar graphs, none of them are functions in the sense of passing the vertical line test, right? They're not functions in the sense of x and y. But they're polar functions in terms of r and theta, right? So these circular or these circular-ish type graphs, you don't really deal with them until Calc 2. But you should have seen them a little bit in Precal, and so we're just kind of reviewing it, kind of bringing what these different shapes are and bringing them back to our memory. We have circles. Now let's look at this next category, which the equations are going to look like this. They're going to end up being, you're going to have some number. That's probably not enough room. Let me move it over. Let me write it a little bit. Let me just put it down here, right? We're going to have r equals, we're going to have some number plus or minus a different number, and then either a sine or a cosine. But again, it's just going to be a 1 theta. And that's kind of our general formula. In all of these are all called limicons, right? That little C has the little kind of weird French accent on it. Limicons, that's how you pronounce it. But r equals a, some number, could be a plus or a minus, and then b, again, a coefficient, could be a sine or a cosine, and it's important that it's just a 1 theta. This is going to be our category of polar graphs called limicons. Let's go kind of look at what some of these limicons are going to be. Let's do the first one, 2 plus 2 cosine theta, and then we'll kind of tinker around with the numbers and the sines and the cosines, and let's try to see how these different graphs end up looking. I'll switch this out, right? So let's go back to y equals, and then let's do that first one, which was 2 plus 2 cosine theta. Let's look at this right here. It's a special type of a limicon, right? It's kind of like a circle, but it looks like it's kind of been pushed inwards a little bit from that left side. Kind of looks like it's been indented a little bit, and it's actually pushed all the way back to the pole, to that origin. And we call this graph a cardioid. It's a special type of limicon that gets pushed back to the origin, to the pole, and it actually ends up creating a kind of heart-like looking shape, and that's called a cardioid, right? Because of the shape of a heart, right? Cardioid. Now, how you could get this without a calculator, the R equals, and that number, that's essentially kind of where you start, right? R equals 2. If you were to ignore all that stuff, R equals 2 would be a circle. So that's essentially kind of what we are setting everything out as. R equals 2. Now, the positive and the cosine, or later, if I had a negative and a sine, right? The cosine or the sine, that's going to tell you, again, which axis we're going to primarily be kind of focusing and working towards. And the plus or the minus just tells you which direction. So just like the circle, sine or cosine tells you the axis, the plus or minus is going to tell you the direction. But really, these two numbers, the A and then the coefficient B, those two numbers are the things that end up deciding which type of limicon graph it is. And the A is how far you set it out. And this B value, I like to think about as how far we push inwards on it. Right? We have the set push relationship, and that's how we can always get these limicons. We're going to set it out to, then I'm going to push in the positive x direction. That means to the right, but I'm going to push 2 units to the right. Now, what's important is that if I'm pushing in the x direction, those 2 points on the y-axis, they actually don't move, right? If I'm pushing horizontally, only the left and the right side move. And later, if I'm pushing vertically, only the top and the bottom will move. But I'm going to push in the positive 2 direction. That means that point is going to slide, and it's going to be pushed 2 units to the right. So that point that was originally at 2 now is going to be at 4. That point that was originally at -2 is now here. And then we end up having this graph that looks more or less like that. It's a cardioid. It's kind of a heart-shaped graph. Now it's rounded on that right side, but it's indented. Since I set it out to, remember the constant is how far you set it, because R equals 2, that's a circle. That's kind of where we start. And then the coefficient, that's how far we push. If I set it out and I push it back the same, that means we kind of indent it all the way back to the pole. But we don't come shorter, we don't go farther, it comes exactly back to the pole. And those are actually a special type of limicon called cardioids, right? Just like how every square is a rectangle, right? Squares are just special rectangles. Cardioids are just special limicons. But every cardioid is a limicon. It's the one that's been set out a specific number and then pushed back that same number. Let's look at the one underneath it. Let's do 2 plus 2 sine theta. Now let's try to graph it before we look at the calculator, and then we'll hopefully just use the calculator to try and reinforce. The R equals 2, right? That's the circle. That's kind of what we set everything out as. And then I'm going to push in the positive y direction. I'm going to push it 2 units up. Now, if I'm pushing vertically, the left and the right points don't move. But that point is going to move up 2, and then this point is going to move up 2. And so here you're going to end up, sometimes it's hard to draw these polar ones. You're going to end up with this cardioid that's mostly on that positive y-axis, right? Again, positive sign means it's mostly going to be in that positive y-axis. If it would have been negative, everything would have been reversed. Let's just flip back over and let's go tinker around with the calculator for a minute, right? There was 2 plus 2 cosine, right? We had that cardioid that was mostly on the right. Notice it's at 0, then it goes out to 4 because 2 plus 2 is 4. If I would have changed this instead of a cosine, if it was a sine instead, right, it would be on the y-axis, right? I would set it out to, then I would push it up to, the horizontal points don't move, but the vertical points, the one that was originally down 2 units gets pushed, it's at the pole. The one that was originally up 2 units gets pushed up, now it's at 4, right? So there we go, 2 plus 2 sine theta, it's on that positive y-axis, and it's a cardioid since the 2 numbers matched. What would happen if we changed it? What would happen? Oops, I don't want the negative. That one I actually need the minus. What would happen if I did 2 minus? Well, I would still take that circle, and then I would push downwards on it. So this one's going to end up being on the negative y-axis. Or if I were to have had something like 2 minus 2 cosine, that's going to end up being on the left side, right? And what's important is that those numbers match. I could have 5 minus 5. As long as those numbers match, right, I set it out 5, I push back inwards on it 5, and if I set it out and I push it back the same amount, you're going to end up at the pole, right? So if, again, the sine or the cosine, that's going to just tell you which axis. And then the plus or the minus is going to tell you which side of the axis. If I had a positive sine, this is going to be primarily on that top side, right? It's going to have some horizontal elements to it, but it's primarily kind of on that positive y-axis. Again, that circle, this circle, like r equals 5, that kind of is what we set it out as. Then we're going to push upwards in the y direction, the positive y direction. We're going to push up. If we're pushing up, the horizontal points don't move. If I'm pushing horizontally, the vertical points don't move. But we set it out, the first number, and then we push backwards with the constant. Again, sine or cosine tells us which axis, and then the positive or the negative tells me really which way I'm pushing, which side of the axis am I going to end up with the majority of my graph kind of focused around. And then what's important is that for a cardioid, those two numbers will match. Okay, so here we go. All right, let's switch it back to the notes. Come on, smartboard, you can do it. This first type of cardioid, right? The relationship between A and B is what's important, right? If A equals B, those are when we're going to have the cardioids, right? If you set it out and you push it back the same, you're going to end up having a cardioid. Now let's look at the other two cases, right? Because we have the case, well, okay, what if those numbers aren't the same? What if my coefficient A is, what if the constant A is less than B? And then the last case, what if I set it out a bigger number, then I push it back? Let's go look at those different types of situations. All of these are limicons, but the ones where A equals B, those are the special type of limicons called cardioids. Let's go look at what happens now based on that changing relationship, right? If the constant is bigger than the coefficient, or if the constant is smaller than the coefficient. Let's go look at these ones, right? Again, sine or cosine is basically going to tell you which direction we're pushing, right? We're going to start with like r equals 1. We're going to start with the circle, and then the positive sine or the positive cosine. That's going to tell you which way and which axis we're going to be pushing on. But we set it out the constant, and then that coefficient is the push. What happens if I set it out 1 and then end up pushing it back 2 units? Let's go look at this one. 1 plus 2 sine cosine. Let's go back to this guy, clear that out. I got 1 plus 2 cosine theta. Remember, we're going to set it out 1, but I only set it out 1, and I'm going to end up pushing it backwards 2. Let's look at this. And here we go. Again, it was a positive cosine, so it would make sense that it's primarily on that right side of the x-axis. But if I set it out 1 and I push it back 2, we actually end up pushing it not just to the pole, but we actually end up pushing it past through the pole. And so what happens is we end up creating this little cardioid, not a cardioid, we end up creating this limicon with an inner loop. Right, let's look at these notes. Again, the constant, the number, is how far you set it. Come on, Bing, you're really struggling today. Come on, you're almost done. We're going to set it out 1. Right, so that's the circle that we're starting off with. But if I'm going to push it inwards a bigger amount than I had initially set it, right? I set it out 1. If I'm going to push, right? Positive cosine means I'm pushing to the right. If I'm going to push it 2 units to the right, again, those vertical points aren't going to move. The one that was here gets pushed 2 units, so it's over there at 3. Now this one gets also pushed 2 units, so now that one gets pushed. And since it gets pushed through the pole, you actually end up with this limicon with an inner loop. Really, these graphs, and they're kind of hard to do. It's going to look at like something like this. It's going to look like this. Then it's going to come here through the pole, loop around, then go around, back out of the pole. Oof. And actually, the graph kind of smoothed out for me, so it kind of like saved itself. Since I set it out 1 and I pushed it back a bigger amount, I end up pushing it past through the pole. You end up creating this limicon with an inner loop. Right? So if I set it out, but I push it back a bigger number, so if my constant is smaller than the coefficient, that's going to be a limicon with an inner loop. Again, it's all based on that relationship between the A and the B. The A is how far we set it. That's the circle. The B is how far we're going to push back. If I set it out a little and push back a lot, if I push back more than I set, you push it through the pole, and that ends up creating that little inner loop. So look at the next one. Here we go. We're going to set it out 1. Again, we're going to start with this circle, and then we're going to push it here in the positive y direction. We're going to push it 2. If I set it out 1 and I push it back 2, again, if I'm pushing vertically, the horizontal points don't move. But here, that one's going to go up 2 units. So that one started at 1, now it's at 3. This one, since I set it out 1, gets pushed up 2. It gets pushed through the pole. And so this one, gosh, I really hate doing these ones with the inner loop. It's going to end up looking something more or less like that. Again, the positive sign means it's mostly going to be on that positive y-axis. If it would have been a negative sign, then I would have been pushing downwards instead of vertically. But what's important is that here for these limicons, if the number is smaller than the coefficient, if the amount that I set it is less than the amount that I push inwards, you're going to end up with this inner loop. Right? So which ones have the inner loop? Well, it's the ones where the coefficient is bigger than the constant. Remember, the constant is how far I set it, and then the coefficient is how far I push it. Right? Always remember, set, push, set, push. That's how I remember how to do these limicons. Let's go tinker around with the graph just to kind of look at a couple more, and then we'll kind of be okay. Right there we had the 1 plus 2 cosine. The next one that we did was 1 plus 2 sine. And so let's go look, right? I set it out 1, pushed upwards 2 unit, had that little inner loop. We could also do something like, how about, let's do 2, let's do minus, let's do 3. Actually, let's do 4. Let's do 2 minus 4 sine. Now, if it's a minus sign, it's going to mostly be on that negative y-axis. I'm going to set it out 2, push downwards on it 4. But since I set it out 2 and push downwards 4, I'm going to push it past and through the pole. So it'll create that inner loop. Again, the negative sign tells you which way you're pushing, and then resultingly which axis and which side your graph is mostly going to be around. Right? The negative sign is going to be mostly on that bottom. Or here, if I did something like 5, let's not do 5. How about 3? Let's do minus 5. Right? The coefficient must be bigger for you to have that inner loop. Set it out 3. Right? Think about the circle. It's 3 units, right? The circle at the origin with 3. Then I'm going to push to the left 5. That means the point that was on the left at negative 3, it's going to get pushed to negative 8, right? It gets pushed to the left 5 units. The vertical points aren't going to move. You got one up at 3, you got one down at 3. Those aren't going to move. But you got that point that was on the right side of the circle. It was at 3. It's going to get pushed to the left 5, so it's going to end up at negative 2, right? Try to visualize it, and boom, there it is. We started with that circle, right? We started with the circle 3, and then we're just going to push to the left 5 units. So that point right here got pushed to the left. This point got pushed to the left. But since I set it out 3 and I pushed it inwards 5, since I pushed it more than I set it, it goes through the pole and you create that little inner loop. Okay, so there's kind of the second category of limicons. If the number is if the number is less than the coefficient, right? If I set it out a little and then push it back a lot, right? If the coefficient is bigger, you end up creating that little inner loop. Now let's look at the last scenario. Here I'm going to have 2 plus 1 cosine. Here that number is larger than the coefficient. Again, let's kind of think about this, right? I'm going to set it out 2. So I'm going to start with this circle that's at 2. Oof, that was just a really terrible circle. Oh well, kind of pretend. Oh, I'm just making it worse. Okay, I regret everything. Let's pretend that's a circle. Now we're going to push in the positive cosine. That means we're going to push in the right direction, but we're only going to push at 1. So that means this point, right? The vertical points don't move if you're pushing horizontally, but this point gets moved 1 to the right, and this one, which originally set out 2 units, only gets pushed back 1. And so what's going to end up happening is that I'm not going to have a circle anymore. This thing is going to look kind of like this, right? It gets extended like this, and it's kind of like this, but it actually gets like indented a little bit. Now, my drawing is more noticeable than what the calculator is going to look like. But what happens was we took that circle, and since we pushed inwards on it a little bit, we're going to end up with this thing, which is called a dimple, right? We're going to end up here with that little dimpled limicon, or that limicon without a loop, right? I get pushed inwards in it on it a little bit, so it's got that little dimple. But since I set it out more than I pushed it back, I don't get all the way back to the pole. If I set it and I push it the same, I get exactly back to the pole, right? I set it out 5, push it back 5, set it out 2, push it back 2. I end up going exactly to the pole, but no farther. Those are the cardioids. If I set it out a little and I push back more, if the coefficient is larger, We push it through the pole, that creates the inner loop. If I set it out more, then I push it back. We do end up having this janky looking circle that gets like indented. It's got that dimple, but it does not go back to the pole, nor does it go through the pole, right? It just has that little indentation. Kind of looks a little bit almost like an apple, right? You know how like what the bottom of an apple, you got the little like legs, like little prongy things. If you take a calculus 3, you'll do 3D stuff like that. But the idea is that it's dimpled. It's just pushed inwards on it a little bit, but it doesn't go all the way back to the pole, nor does it go through it. Let's look at that one. It was 2 plus cosine theta. We set it out 2. We're going to push to the right 1. This one's even kind of hard to tell. But if you look kind of this left side, it's a little bit flatter. Let's see. Let's mess with the window. We probably don't need negative 16 to 16. I guess it's because I did the zoom 6. Let's just do something like negative 5 to 5. That's probably going to be okay. And let's do negative 5 to 5. Right, again, this may not look super nice. It looks kind of more ovular-ish or ovular-ish. But notice that left side, right? It's kind of a little bit flatter because I had set it out 2 and I got pushed back 1. And so that dimple isn't like super noticeable. A lot of the times in my diagrams, I'll kind of make it more visually noticeable. But yeah, there it goes, right? It doesn't have to look super precise, super pretty. But the idea is if I set it out and then I push it back a little bit, but if the amount that I push, the coefficient, b, if that's less than the amount that I set it out, the constant, if the coefficient is less than the constant, you don't push it all the way back to the pole. You don't push it through the pole. So there's no inner loop. It's not a cardioid. If I push it only a little bit, you will have that little indentation, that little kind of flatter side. And we call that a dimpled limacon, right? So you could call it a dimpled limacon, or you could call it a limacon without a loop, or a limacon without an inner loop. If you say dimpled or if you say without a loop, that's the same, right? I like to say dimpled because I think that's kind of fun. But limacon without loop or limacon without inner loop, that's really the same thing as saying a dimpled limacon. You push inwards on it, but you don't push all the way back to the pole. Remember, the coefficient A is how far you set it out. The number A is how far you set it out. And then the coefficient, that's how far you push, right? Set, push. If I set it out more, then I push inwards on it, I will not make it back to the pole. The cardioids are the special times, right? If I set it out and I push it back the same, I push it back to the pole exactly, but no farther. If I set it out a little and I push it back a lot, if I push more than I set, you push it through the pole, which creates the inner loop. And then if I set it out a lot and only push back a little, you do not get to the pole, but you create that little dimple. Let's do this last one. Here you go. R equals 2. Slightly, well, nope, I was going to say slightly was terrible, and then I ruined it in that top right. Here we're going to push in the positive y direction, but we're going to push 1 unit up. That means the horizontal points don't move. This one gets moved up 1. This one gets moved up 1. And so again, we're going to end up with this thing that's like kind of a little bit dimpled on that bottom. Wow, that one actually, that one needs to be framed and put in the Louvre. That's a great drawing, Mr. Bell. Oh my gosh. Okay, that's like the best graph I've probably ever done. Okay, I'm just kidding. I'm hyping myself up. But these polar things are kind of a little bit weird and not super fun to graph. But the idea is all of these, the cardioids, they're just a special type. But the limacons with and the limacons without a loop, all of them, they're really kind of based on this equation, right? That's your general formula for all the limacons. And it's the relationship between those two numbers that dictates what type of limacon it is. If the A and the B value equal, right, those are cardioids. If I set it out more, then I push it. So if A is bigger, then that means I set it out a lot, push it only a little bit, I get the dimpled limacons, or the limacons without loop. Or if I set it out a lot, or if I set it out a little and I push back a lot, if my coefficient is bigger, then I end up pushing it back through the pole and I get that inner loop. Which graphs go through the origin? Well, those would be the cardioids. Cardioids, there we go, and the inner loop ones. Cardioids and the inner loop ones. Which ones do not go through the origin? Well, those would be the dimpled, right? And then which ones have the inner loop? It's the ones where you set it out a little, but you push it back a lot. The ones where the coefficient is larger. But all of these are called limacons. Again, cardioids are just a special type. And there's your general formula. If you remember set push, that this circle is kind of what you start with, and then the positive cosine, or it could be a negative sign, that's how far we push inwards on it. The positive or the negative, the sine or the cosine, that tells us which direction we're pushing. And if we remember set push, we're pretty much able to graph any of these limicons. A, the number, that's how far you set it. The coefficient, B, that's how far you push it back. Let's go look at just a couple more, and then we'll kind of be done. All right, let's go do, we had a positive cosine. Let's go look at the one that was the positive sine. Ooh, messed it up. Oh gosh, okay. 2 plus sine theta. Oh no, no. What am I doing? There we go. That's what I wanted. Let's graph this one. So that one, you can tell it's like flat on the bottom because it was a circle. It got pushed upwards 1. You can see that point is up 1. This point was originally here, got kind of pushed up. It's got that little kind of flat, kind of potato-y edge. It's got that little dimple. Or if we were to do something like a little bit more noticeable, we could do, how about, let's do 3 plus 2. So I can insert, nope. What am I doing? Okay, come on. Here we go. Let's insert, nope, that's too far. Insert, how about 2? If I set it out 3, and I only push back 2, as long as the coefficient is less, that's going to create the little dimple. Now notice that dimple is a little bit more noticeable, right? It's not super flat. If I had something like, let's do about 4 and 3. Nope, let's do a negative. How about 4 and 3? So I'm going to set it out 4, push back 3, and since it was a negative, right, now I can see that dimple's a little bit more noticeable. Right. When it was just 1 and 2, it looked kind of just flat, but it really was a dimple. You just have to kind of look at the different scale to see it. Again, if I set it out a little, or it doesn't even have to be a little, but if I set it out a number and I push back less, then I don't push it back all the way to the origin. Right. I get just that little dimple. So there we go. Right. The different types of limicons. Those are kind of the hardest, I think. But yeah, those limicons. You can have cardioids, that's when A equals B. You can have the inner loop, that's where you push it back more than you set it. So if the coefficient is bigger, that's the inner loop. And then you can have the dimpled ones, the ones without limits, the ones without loops. That's where the coefficient is smaller. Remember, the number is how far you set it. Coefficient is how far you push. Sine or cosine tells us which way we push. Positive or negative tells us which way we push, right? That kind of also tells us which side of the axis, and which side the graph primarily ends up being around. Yeah, there we go. Hopefully that makes sense. Hopefully this is kind of bringing back some of that pre-cal stuff from a couple years ago. But I'm trying to go just really, really, really fast. All right, now next page, we're going to have these things called rose curves. So let's go look at these. These are all going to end up being rose curves. And the general formula for the rose curves, we don't have that constant. We just have the coefficient. It could be a positive or a negative, and it could be, actually, we don't really ever have the negative ones. So it's really just going to be the coefficient, and then it could be a sine or it could be a cosine. But what's going to be different is now I've got a number in front of that theta. Right, so here we go. We've got R equals, I've got a coefficient B. I don't want sine divided by cosine. I don't want tangent. I want sine or cosine. Oof, it's a rough day for me. Sine or cosine, and then we have in theta. Let's go look at what that different in value does. All right, here we go. We got 2 cosine 3 theta. So this one's different because it's not just a 1 theta. Let's go look at it. We got 2 cosine 3 theta. 3 theta. There we go. This is going to be a rose curve. What's important to note, how many petals and how long each petal is. It's kind of nice to know where the petals are, but ultimately that's not terribly important. But the cosine graphs will always have 1 petal on the x-axis, and it's usually always going to be on that positive side of the x-axis. But since I had 2 cosine 3 theta, right, that 2 tells me the length of the petal. Each petal goes 2 units. That goes 2 units. That goes 2 units. That coefficient tells me the length of the petals. And then here, the in value, that told me that I had 3 petals, right? It was 3, which was odd. I had 3 petals. Let's go look at the next one, which I'm not going to flip back to the notes. I'm just going to tell you. The next one is 2 cosine 5 theta. What if I change it from 3 to the next odd number 5? Oh, there we go. It's another rose curve. Each petal is 2 units long, and then it's got 5 petals. Or if we wanted to change it, and if we had 3 cosine 5 theta, now the petals are going to be 3 units long. Right? The coefficient tells me the length of the petal. All of those petals, this one, let's try to zoom. Let's zoom it square. Let's zoom square back to the That didn't help. It looked kind of janky, right? These are really actually smooth, kind of circular graphs. They look kind of pixelated and stuff. That's just whatever aspect ratio you happen to be looking at your window. But that coefficient ends up telling me the length of the petal. And then that number n, the coefficient of the theta inside the argument, it's going to tell us how many petals there were. When the coefficient was 3 theta, I had 3 petals. When it was 5 theta, I had 5 petals. Let's go back and let's do some sine graphs though. These cosine ones always have one on the positive x-axis. Right, let's go graph the first 2, and then we'll come back to the calculator. Okay, so here we go. These ones are kind of hard to graph, but really what would happen? The 2 cosine 3 theta, that first one's here. Really what this graph does is it does this, then it does this, and it does that. Oops, yeah, there wasn't one down there, right? Oops, it was kind of over here. It was like this. Oh, that was a lot bigger than 2. Yeah, there we go. It's kind of like this. Right here. Then we had the other one, which was like up here. Then it actually completes that last one. It usually starts on this side, and then it's going to go through. That was terrible. It usually starts. This one was 3, so it usually kind of goes something like this. This one was 3, so it's like this, and then this. Let's see, this one. No, I messed it up. Oh my gosh. Yeah, it's kind of hard to trace it. If you actually, let's go watch the calculator trace it. Let's see. So I'm going to hit window. I'm going to turn this theta step. Right, that's changing how often, how frequently it's plotting the points. I'm going to make this smaller, which is going to make it graph slower. Let's try 0.05. Let's see if that works. Sometimes I make it too slow and it graphs really. I make it too small and it graphs really slow. But if you change this theta step, the smaller it is, the more points it's going to graph, the longer it's going to take, the slower it is. The bigger that is, the fewer points. Here we go. Oh, that was too fast. Okay, let's go change the window. Let's go change that theta step. Let's try 0.0. Oops, I don't want point. I want 0.00. Let's try 0.001. I feel like that's going to be too slow. Nope, there it goes. Right, you can kind of watch the order in which it graphs. And then Mr. Bell was like really terrible at emulating it. Again, let's go turn that back on. Come on, let's go to the y equals. What are you doing? What are you doing? Oh no, it's frozen. It's still going. Oh, it's still going. That's why. Here we go. So if we did 3 cosine 5 theta. Okay, it's still going to do it. Let's turn it off. And then we'll turn it back on. And then let's watch it, right? It's going to start over there, then the pathway that it traces. It's kind of nice, right? It doesn't do one petal, then move on to the next. Actually, it kind of starts off with that first petal, then it kind of goes around, and it's actually going around a second time, which is why it's kind of weird. But there we go, right? We have this rose curve that with the coefficient for the whole function was 3. That tells me the length of the petals, and then the 5, that told me how many petals there were. Let me try to draw this and have it not be super terrible. We had the first petal, and then the second petal ended up being kind of over here, and then it was over here. Ooh, that was, oh gosh. Okay, here we go. Well, in theory, all of those are supposed to be symmetrical. Wow. Okay, this is just terrible. This is just really a travesty. In theory, all of the petals are congruent. Right, my diagram, the first one's not bad. This one was really terrible. But all the petals are congruent. Right, petals are all congruent. They're all the same length. And what's nice is that they are equally spaced too. Right, they're all going to be equally spaced around that pole. Right, the whole pole is 360 degrees. So if you know there's 5 of them, 360 divided by 5, that's going to tell you the angle. It's going to tell you what that angle between each one is. But all those petals are equally spaced. They are congruent, right? And this number right here, that tells me the length of each petal. Length of the petals. Now, it's this one that tells me how many petals there are. How many? Oops, that's not how you spell how. How many petals? Now, let's go look, right? When the coefficient of the theta was 3, I had 3 petals. When it was 5, I have 5 petals. Let's go look at what happens. I guess we need to do the sines and the cosines first. Okay, let's go do the sine ones. Switch it back. Let's go change this. Let's go change it to sine. The first one is 2 sine 3 theta. So here we go. 2 sine 3 theta. There we go. And it's going to go graph this, right? 3 theta, it means there's going to be 3 petals, but notice one of them is on that negative side of the y-axis. So there we go. That one kind of looks like that. And then if we were to change it, it's still graphing. Let's quit out of there. Come on, come on. You can do it. Come on. There it goes. It was going around again, right? It was actually going around 3 different times. But here, if we were to change it, let's do 3 sine 5 theta. Bam. This one's going to end up having 5 petals. But notice, one of them, instead of it being on the bottom side of the y-axis, now there's one on the top side. If you kind of look, right, you can kind of see it. The thing is still going around and around. It's actually, because it's a periodic function, it's going around and it's tracing that graph multiple times. I could put the little football on the graph to watch us, but yeah, it's just going around multiple times, which is why it was not letting me quit out of there. Here, I think it should be done, so it's letting me quit. But yeah, there we go, right? That's we got the 3 petals and we got the 5 petals. Let's go do those 2. Let's see, which one do I want to do? I want to go back to here. So we go, the 3 petals. You actually had one that was down on the underneath. Oops, that's not the marker. You had one here. Oof, that was just really bad. There was one, and then the other ones were equally spaced. So it looks something kind of like that. Oh well, in theory, again, they should be symmetrical. And then this one went up to 3, and then we had the other 4 petals, which were equally spaced. You had one here, kind of one here, and one there. Again, the petals are supposed to be congruent. Mr. Bell's just like abysmal graphing and drawing skills are just on display here. It's a lot harder on the smartboard than you think, right? It's actually mildly easier on paper and pencil, but yeah, pretty terrible. Petals are congruent and equally spaced. Now, when you have that coefficient that was 3, we had 3 of them. When it was 5, we had 5 of them. If I changed it, and if I put 7, there's going to be 7 of them. I'm going to go do this theta step, and I'm going to make it bigger, so that way it goes faster. If you have a 7 theta, there's 7 petals. Right? What's important is that if that coefficient of theta, if it's odd, that is exactly how many petals you're going to have. But let's go back to the notes and let's look down here. What happens if I have 3 cosine 2 theta? Let's see what happens there. Let's go back to here. So 3 cosine 2 theta. Let's graph it. Notice I don't have 2 petals. I have 4. So there we go. It's kind of weird, right? When I had an odd coefficient of that theta, I had equally that many petals. But if I have a 2 theta, I have 4 petals. And the next one is 2 cosine. Let's try 4 theta. That's the next one in the notes. Now, with the coefficient of that theta being 4, we have 1, 2, 3, 4, 5, 6, 7, 8 petals. Okay, so if the coefficient is odd, that's how many petals we have. Right? If n is odd, you actually have n many petals. 3 theta meant 3 petals. 5 theta meant 5 petals. 7 theta meant 7 petals, right? If n is odd, you have that many petals. But if n is even, you actually have 2n many petals. You have twice as many petals. When the n was 2, we actually ended up having 4 petals. Right? And one of them is on that positive x-axis. And then because of symmetry, since there's 4, they're all 90 degrees apart. But when I had the 4 theta, you actually had 8. So we had 1, 2, 3, 4. And then because of symmetry, we need to fit those other 4 in. They're all going to be 45 degrees apart. But if you have an even coefficient, you have twice as many petals. Right? So let's go do 3 sine 2 and 2 sine 4. Let's go do those last ones. And then we'll kind of be done with most of these graphs. Yeah, I'm taking a long time today. Oh well. There's a lot to get through today. Let's do the next one. Is 3 sine 2 theta. Here we go. That's also going to be 4 petals, but notice none of them are on the axes. Right? But 4 petals because my coefficient was 2 theta. And then let's do 2 sine 4 theta. Again, 4 theta is going to give us 8 petals. So let's go do those last 2, and then we'll be done with the rose curves. Here we go. That one, we had the 3 petals, the 4 petals like this. Again, equally spaced and congruent. So they're all 90 degrees apart, but they're missing the axis. And then here we're going to have 8. And so this one's going to kind of look like this. We have 2 in each quadrant. I've done worse. So what do we notice about these graphs, right? The important takeaways. The coefficient out in front, that number, that's going to tell us the length of the pedal. The sine or the cosine really tells us where the first pedal is going to be. If you have a cosine graph, there will always be a pedal on the right side of the x-axis. If it's a sine graph, sometimes you have a pedal on the y-axis. Sometimes it's on the bottom side, sometimes it's at the top. It actually flips, right? The 7 theta had one on the bottom. The 9 theta would have a pedal on the top, just like the 5. But really that sine or the cosine just tells you where the first pedal is going to be. But what's important is that those pedals are congruent and equally spaced. And so the length of the pedal is the coefficient out in front, and that n, the number in front of the theta, that tells you how many pedals. If the n is even, you have twice as many pedals. If the n is odd, we have that many pedals. Okay, so those are the important takeaways. All right, now let's go look at these last couple of ones. Those are our Rose curves. And then we have a couple other graphs, and then really these are not as important. But we have r squared equals 4 cosine 2 theta, and then we end up having the r squared for sine 2 theta, and then we have the r equals theta. If we were to look at these are actually going to be called lemniscates, right? They're lemniscates, and that's coming from, I think, Greek. I can't remember if it's Greek or Latin. The Greek, I think it's Greek. The Greek word for lemnos actually means infinity. And so lemniscates are these graphs that essentially are like half of a Rose curve. Let's go for it. R squared equals 4 cosine 2 theta. Let's go graph these. Let's look at what this lemniscate is. Let's clear that out of there. Actually, I need to quit out of there. Now, I can't do r squared, so I'm going to have to do the positive square root, so second square root, and then I can type in the 4 cosine 2 theta. Close that one, so that's going to get the positive side, and then of course we're going to need the negative square root of 4 cosine 2 theta. Now for these ones, if you were to graph it right now, there's usually going to be some empty space, and that's so yeah, so it's doing kind of both of them. But there we've kind of got this infinity-like symbol, but it looks like there's empty space. If you were to change your theta step, and if you were to make that theta step smaller, like let's try 0.01. Usually the smaller that theta step is, the more solid it's going to be. But this one's going to end up being that little horizontal infinity sign. And then if we were to change it so that instead of the cosines, if instead I had sine, where is it? There we go. I have the sine and then the sine. It's just going to be diagonal instead of horizontal. But again, the theta step actually is kind of going to fill in the gaps. These don't have any weird holes, but these lemniscates, again, that tells me really how far it's going to end up going. Well, the square root of 4 tells me it's going to go to 2, and then on the other side, and so it ends up looking like an infinity sign. And then with the sine is actually kind of diagonal. So that's how we end up getting the Rose curves with only 2 pedals. They're technically lemniscates. Yeah, they look like the infinity signs. That's hence the name, lemniscates, based on the word lemnos, which is the infinity sign. And then the last one, r equals theta. The lemniscates and this last one, they are not terribly important. It's the cardioids, the circles, and the Rose curves that we see frequently. This last one is r equals theta. If you were to graph it, it's called the Spiral of Archimedes. And it would actually keep going. If I were to change this, see it's got from theta, it goes from 0 to 2 pi. If I were to change this to 4 pi, it's gonna graph more. Right? It's gonna keep going, but this r equals theta, that's your last real graph, the r equals, that's your Spiral of Archimedes. It kind of looks like this, kind of goes like this, then it kind of comes over, then it goes like this, and then it would keep going, right? And really the ratio of that is based on the Fibonacci sequence. Yeah, there we go. We're not going to get too far into that. But the lemniscates, they are half of a Rose curve with 2 pedals. They look like the infinity sign, and then it's always that's always going to be squared, and it's always going to have the 2 theta argument. And then the r equals theta, that's your Spiral of Archimedes. These ones aren't super common. In fact, I don't really think I've ever seen. Actually, I've seen a lemniscate on the AP exam like once or twice, but they always just give us the equation, and it's always a calculator question. But yeah, those ones are not as common as the lemniscates, the circles, and the Rose curves. Okay, we're taking a long time today, but hopefully all this stuff, none of this in theory should be new. It should be review of what you saw in pre-cal, but you probably just don't remember it from 2 years ago. But let's go. We got a little bit more to do today, and then maybe we'll just find a good stopping point. All right, let's finish the pre-cal review at least before we end it today. So we have the polar form, which is based on r's and theta. And then we have the rectangular, aka the Cartesian form, which is based on x's and y's. Can we plot points when it's in the polar form? Yes, but typically they're on the polar axis, which is a circular-based axis. So if we're going to plot points, instead of doing the x, y, right, instead of doing the x first and then the y, we actually usually do the angle first. And then a positive radius, that positive number, is either going to go towards that angle, or a negative radius would go directly away from it. So if we're going to plot this point 4 2/3, 2/3 is right here, and then you would go 1, 2, 3, 4 units in that direction. So there's my point A, right? Find the angle, then if it's a positive radius, you go directly towards it. Then if I were to do the point B, 7/6, that's going to be this direction, right? Here's my ray, there's my direction, 7/6, and you're going to go 3 units, 1, 2, 3, 3 units in that direction. Come on, smartboard. So that one's done, and we had that one done, so very good. Let's go look at the next couple. 5/4, if we rotate it, 5/4 is going to be right here. That's 5/4, and then I'm going to go, -2. So actually, instead of coming in this direction, instead of going towards it, I'm actually going to go in the direct opposite direction. So -2 is going to be 1, 2 units directly away from my direction 5/4. So that's where the point C would be. And then the last one, -π/6. -π/6 is coterminal with 11/6. So there's my angle, and then a positive radius goes towards it. So really what you want to do when you're graphing polar points is you figure out where's my direction, what's my angle. Could be a positive angle. Positive angles rotate counterclockwise. The negative angles rotate clockwise. I figure out my angle, and then the positive radius will either go in that direction, or the negative radius will go exactly in the opposite direction. So you can go towards your point, or towards your angle, or away from it. The negative radius, that's when you go away from it. And then from pre-cal, right, again, everything is kind of based on right triangular trig. We have x, y, and really this is right for any arbitrary point, x and y. This is the whole basis for the unit circle, and so therefore of the polar. If I wanted to find code, remember we have SOHCAHTOA. Trying to go fast. SOHCAHTOA cosine is adjacent over hypotenuse. So it's going to be x over y, not x over y, x over r. And so if I wanted to get an equation for x equals, multiply the r over. So it's r cosine theta, right? Cosine is adjacent over hypotenuse, x over r. So x is r cosine theta. Now the sine is opposite over hypotenuse. So that's going to be y over r. So again, multiply that r over. Y will be equal to r sine theta, right? Cosine's x, sine's y, and you just need to remember for polar, it's r cosine theta, that's x, r sine theta, that's y. And then for tangent, tangent's opposite over adjacent, so that's y over x. Right? We don't typically fuss with the tangents, although we do frequently, if we have to find the angle, typically we'll do an inverse tangent of y over x. Right? That's how we can usually find our little reference angle if we need to, inverse tan. But because of Pythagorean theorem, we know that x squared plus y squared is going to be equal to r squared. Therefore, r is the square root of x squared plus y squared. Could be plus or minus, but usually we just use the positive root. But the important things to remember from polar: x is r cosine theta. Y is r sine theta, x squared plus y squared equals r squared. Those are the big things that hopefully you should remember. And if you do remember them, they enable us to convert back and forth between coordinate points, being rectangular to polar and from polar to rectangular. And then also we can translate entire equations. All right, let's keep going. I just want to try to get through, and we're not going to get to the calculus stuff today, but I at least want to finish the pre-cal, which is just these two examples in the top of the next page. Yeah, oh well. Let's finish the pre-cal, and then I'll just make a video for the calculus stuff, and then you can just watch that later next week. Here we go. Convert this polar point to rectangular. Here we go. Remember, rectangular means x and y, but x is just r cosine theta. The r value is 2. The cosine plug in the theta. Let's see, 5/6. 5/6 is over here, where you come over a lot, up a little. So it's negative root 3 over 2, 1/2. So the cosine of 5 pi over 6 is going to end up being negative root 3 over 2. Those 2's will cancel. So there's my x value. It's the negative root of 3. Right? It's pretty simple. You just plugging it in. And then we would just need to do the same thing for the y value. But y is r sine theta. So this is going to end up being 2. And then I'm going to need the sine of that angle. So I have 2. And then the y value of that point was 1/2. The 2's cancel. So that y coordinate is 1. So then the answer to this question, right, if I wanted it in an xy coordinate point, the x value was negative root 3. The y value was 1. So if you know x equals r cosine theta, and if you know y equals r sine theta, then switching it from polar to rectangular is very easy. You just have to know some unit circle stuff also. But what if we wanted to switch backwards? What if it gave us an xy rectangular or Cartesian point? And what if it wants us to switch to polar? So it wants us to have r theta. Well, typically I like to find the r value first because I think that's the easier thing to do. But let's graph it. It's going to go 1, 2, 3 units to the right, and then 1, 2, 3 units downwards. So that point's going to end up there, right, where it's 3, negative 3. And then really what I have, right, I have that x dimension, which was 3. I have this y dimension, which was negative 3. And then the r value is just the length of that hypotenuse, which if you remember back up here, is really just Pythagorean theorem, right? So here r is going to end up being the square root of x squared plus y squared. And really, we don't ever want those hypotenuses to be negative. We always want them to be positive. We're assuming that we're going to have the positive r. So that's 9 plus 9. So we're going to have the root of 18, which is 9 times 2. 9 times 2. So then we're going to end up having 3 root of 2, right? There's my r value. If you wanted to leave it as root of 18, that's okay. But that radical simplifies a little bit. But I got the r value. It's just Pythagorean theorem. The square root of x squared plus y squared, right? That's Pythagorean theorem. Now, finding the angle is a little bit harder, right? We know this is now 3 root 2. If you remember that 45, 45 special right triangle from geometry, you would also be able to get that really quick. But here's just a right triangle trig, which you could have done from geometry. You know the adjacent and the hypotenuse, so you could do an inverse cosine. You also know the opposite and the hypotenuse, so you could do an inverse sine. But typically what's easiest is for us to do the opposite and the adjacent side and to just do an inverse tan. But really, once you have that little reference triangle completed, it doesn't matter which inverse trig you do. But most of the time, you're going to set up the tangent ratio because the x and the y are the things you're given. And they're usually kind of the easier, the nicer of the two numbers. But tangent is y over x, so it's negative 3 over 3. So here I know my tangent is negative 1. And so my theta is going to be inverse tan of negative 1. So then I'm thinking, okay, on my unit circle, there's 2 points on my unit circle where the tangent inverse is negative 1. But because of the domain restriction, I'm not going to want the angle in quadrant 2 or 3. I'm going to want the one here, which, remember, instead of using the big positive angle, which would be 7 pi over 4, instead of using that big positive angle, that's not actually 7. Wait, 1, 2, 3. Actually, it is 7. Instead of using the big angle, we're going to use the negative one instead. And honestly, like, it doesn't matter. When you're naming this coordinate point, polar coordinates are not unique. There's infinitely many points that would land you at that same location. So you could use 7 pi over 4, or if you wanted, you could use the negative pi over 4. Both of those angles are coterminal. So if you were to plot either of those points, remember, you would go toward the angle first, and you'd go towards it. Either one of those would land you at that same spot. You could either rotate that angle and then go your r distance towards it, or you could come the negative angle and then go r unit towards it. You're going to end up at that same point. So it really doesn't matter. I guess generally we probably prefer the one that's between 0 and 2 pi, but if the question specifies something, make sure you just give the angle accordingly. I know I'm going long. I'm sorry. Let's just do a little bit more. Let's do the 2 examples on the next page. This is the stuff that I had really wanted to get to today, because this is how we find the slope of those polar graphs. We're not going to have enough time. but oh well. I will make a video and I will kind of shoot that to you guys later. You'll need this, I think, for the first polar homework. So I will make that video and send it to you. But just for the sake of time, we're just going to do these last couple of pre-cal questions. And then I'll make you guys videos for the slope of the graph and for all the area stuff. And I'll send you that to watch and to do all the homework next week. Don't worry about doing homework between now and next time unless you want to. Just kind of knock out all the polar stuff next week. That's perfectly fine. Finish the vectors and parametric stuff this week. Here we go. Convert the following equations from Cartesian into polar or vice versa. Remember, we have x is r cosine theta. We have y is r sine theta. And we know x squared plus y squared equals r squared. Those are the three big things. So what we would be doing is trying to look for things that I could switch. Like here r, or here y, I could switch it to r sine theta. And so there we go, right? We could leave it like that. Or if you wanted to, you could divide it over. Right? If I have 1 over sine of theta, that's the same thing as cosecant theta. I guess, and I should leave the 4 first. Here we go. Let me put the 4 first. Oh my gosh. 4 cosecant theta. You could leave it like this, or you can leave it like this. Those are both equivalent, right? Whether it's r sine on the left or it's r equals the cosecant on the right, both of those are fine. What type of graph would this be, right? What type of function would this be? Well, y equals 4, that's a horizontal line, right? 1, 2, 3, 4, horizontal line. And that's always what those things are going to look like. If you have r sine theta equals number, or if you have r equals some number cosecant theta, all of those are going to end up being horizontal lines. Horizontal lines. At whatever that number is, right? Y equals 4, horizontal line, just change the y, right? Just using that really basic substitution. There we go. If I would have had something like cosine, right? If instead of it would have been x, right? If I had x equals 4, then I would have r cosine theta equals 4, or I could have r equals 4. The reciprocal of cosine would be secant. So something like this would end up being a vertical line. So r cosine theta equals a number, or r equals some number secant theta. Those are going to end up being vertical lines. Okay, so we could have horizontal lines in polar, or we could have vertical lines in polar. I don't know why I just didn't do this one, right? That's kind of the same thing I just did, right? But there we go, right? That would be a vertical line. I'm just going to pretend that I'm going to use 4. I'm just going to do that right there. I should have really looked down. I figured it would all be the same. Oh well. I guess that's kind of the backwards. Oh well, we'll do that one too. But we could have horizontal lines or vertical lines just based on switching them. And then here, this last one, x squared plus y squared, right? This one changes pretty easily. It's just r squared equals 25, which means r equals 5. And we should know what that is, right? That's a circle with a radius of 5. It's a circle centered at the pole with a radius of 5. Okay, so x squared plus y squared is r squared, and then you could square root it r equals 5. You could leave it like this, but r equals 5 is just so much nicer. So we have equations for horizontal and vertical lines. They can switch back and forth. We have the equations for circles. They can switch back and forth. Let's just do these last 3 really quickly, and then I say really quickly, and then I just end up wasting a whole bunch of time. Let's do these last 3, and then we'll be done. I don't know why I'm doing that. Let's just do that. That's much faster. Here we go. Now we're going to convert the equations from polar to rectangular. Okay, well, look, we're going to again be looking, right? We know x is r cosine theta. So if I saw anything like that, I could change it to x. Or if I saw anything that's r sine theta, I could change this to y. Right? So let's go for it. Here, r sine theta, that's y. And then that's just y equals 3. So again, horizontal line up at y, or up at 3. Right? Horizontal line, not too bad. If we would have had something like, again, we talked about it, if I would have had like r cosine theta equals 2, that would be x equals 2. That would be a vertical line. So we can do, I don't know why, oh no, there we go. So we could have horizontal or vertical lines. That's great. And this next one, we have r equals 2 cosine theta. We've seen stuff like this. Remember, the sine or the cosine is just going to tell us which axis. and that number is going to tell me how far. This is going to end up being a circle, and that one's going to end up going 2 units to the right. So I actually know what that graph is going to look like based on the stuff we did earlier. If you wanted to actually take the equations and switch it over, here's what you would have to do. You would square both, actually you would multiply both sides by r. So r times r is r squared, and then on the right we'd have a 2r cosine theta. And then this, right, r cosine theta, that we could change to x, and then r squared is x squared plus y squared. And you could leave it like this if you wanted to, or we could get all the x's together and we could complete the square, and then we could get all the y's together and complete the square. Let's do it, right? We have x squared minus 2x, and then we have plus the y squared, that's equal to 0. If I were to complete the square with this, remember I take the linear coefficient, divide it by 2, so I've got negative 2 divided by 2, that's negative 1, square it, that tells me the number that's supposed to be there, but if I add 1 on the left, of course, I'm going to keep it balanced. And then this would end up factoring x minus 1 squared plus y squared equals 1. And this is the equation, come on, smartboard, that's the equation of a circle, right? The center of the circle is going to be at 1. That's not shifted at all, so it's the center at 1, 0, which we kind of knew, right? Since that circle was on the right side and it went out to 2, the center's at 1, 0, and then of course the radius is going to be 1. From geometry, we know x minus h squared plus y minus k squared equals r squared. That's a circle with the center hk, and then the radius is r. Radius is equal to r. So like we could switch those and we could complete the square to get the equations, but if you just remember, okay, sine or cosine tells me the axis, the plus or the minus would tell me which side of the axis, we can actually get the graph pretty fast and pretty easy without having to switch it. Last one, and then I promise we're done. I know this has taken forever today. Last one. Here we go. Theta equals 2/3 pi. What you'd want to do here is actually take a tangent on both sides. So tangent of theta equals tangent of 2 pi over 3. Tangent of theta is y over x. And then tangent of 2 pi over 3, let's just go figure it out. 2/3, that's 1/3, 2/3. So 2/3 is here, it goes over a little, up a lot. So it's going to be a negative 1/2 root 3 over 2. Tangent is y over x. The 2's will cancel. So the tangent at that point is going to end up being root 3 over negative 1. So negative root of 3. All right, so tangent of 2 pi over 3 is negative root of 3. And so if I wanted to, I could get it into y equals negative root of 3x. That's the equation of a line, right? It's a line. It's got a slope that's equal to negative root of 3. And that slope is just equal to whatever that tangent value was. It's got a y-intercept of 0. Y-intercept of 0 since it's not shifted. So here it's going to look something kind of more or less like this. And guess what? If I were to think about my unit circle, guess what angle that's going to end up pointing me towards? 2 pi over 3. Right? That's what this angle right here is going to end up being. Right? So theta equals is just a line, and it's a line that goes through your respective angle and the opposite side of it. Right? So it's not just the line that goes through 2/3. That line also needs to go in the negative direction. But here, that's your theta equals 2 pi over 3. So lots of different polar graphs. Right? We have the circles, a couple different types of circles. You can have the circles on the x-axis or the y-axis, or you can have the circles at the pole, r equals number. We have the limicons. We have cardioids, limicons with loop, limicons without loop. Those are dimpled. We have rose curves, which could have an even number of petals. If the coefficient is even, remember twice as many petals, or if the coefficient is odd, you have that many petals. Or we could have the lemon skates, those are rare. We could have the spiral, which is rare. We could have horizontal and vertical lines. We could have diagonal lines, all sorts of different stuff. Right? Hopefully this is Hopefully this is kind of triggering some stuff in your brain from a couple years ago. I know you didn't do a lot with polar. You don't in Precal, right? It's a pretty short topic. You spend like 2 or 3 days on it, and then you go like at least a whole year without seeing it. But it is something that does come up frequently in Calculus 2 and in Calculus 3. So you got to know what these graphs are going to look like. They don't come up a whole lot, but we should be able to deal with them when they do come up. There's lines, there's circles, there's the lemon skates, there's the limicons, And the limit skates aren't really important. I meant to say limicons. And then there's the Rose curves, right? These polar graphs are kind of ugly. If we have a calculator, of course, that helps us. But we really should be able to recognize what all the graphs look like and be able to switch back and forth, either switch coordinate points from polar to rectangular or vice versa. And we should also be able to switch entire equations from polar to rectangular and vice versa. We didn't quite get to the derivative stuff that I wanted to. Oh well, there's a whole bunch of pre-cal stuff that we needed to get through. Hopefully that was beneficial. I will make another video detailing those next two examples, which is how do I get dy dx? How do I get the slope of the graph at any point? It's an ugly formula. But I'll make a different video with that, and I will send that to you. So yeah, thank you guys for hanging in there. Let me